Welcome everyone, my name's Stephen Brooks and I've created the Electrical Protection Part 2 course. I've tried to write the course to make it accessible to everyone, including people without an electrical engineering background. Electrical protection is a key element in all electrical systems and ensures that the electrical network can operate safely and efficiently. This 2-hour-long protection course will introduce you to some more protection systems, with a particular focus on circuit breaker protection, transformer protection, and SCADA. I hope you enjoy the course and get something out of it. Most substations use DC to supply the protection and control systems, so that when the AC supply fails, we can continue to monitor and control the network. In the first section, we look at all of the DC systems that you will come across inside a typical transmission level substation, including the basic architecture of the DC system, and how we size the batteries that keep the supply going. In the next section, we look at circuit breaker protection. We start by looking at the circuit breaker auxiliary switches, which are a key component in any protection system. We then look at the main circuit breaker protections, including trip circuit supervision. As we've said, the circuit breaker is critical for clearing faults on the electrical system, but sometimes things go wrong, and the circuit breaker fails to clear the fault. In the next section, we will look at how we detect this critical situation, and what actions we need to take to ensure that the electrical system is protected from a collapse. When a fault occurs on the system, we trip the circuit breaker and clear it. For certain types of faults in electrical systems, we sometimes want to re-close the circuit breaker to get the customers connected again. This principle is called auto-reclosure, and in the next section, we look at all the auto-reclosure equipment that you will come across. When we close circuit breakers, we have to ensure that the two systems that we are connecting have similar parameters, otherwise the circuit breaker may get damaged. To do this, we use synchronizing equipment, and in the next section, we look in detail at the manual synchronizing equipment that we use, and how the automatic synchronizing equipment gets integrated into the closed circuit. Transformers are the most expensive device that we use on the electrical network. Looking after them is one of the main goals when we design protection systems. In the first of 5 sections on transformers, we look at some of their basic design features, including how we connect the windings, and how these connections lead to different vector groups. In the next section, we will look in detail at how transformers are constructed, and how the cooling system of a transformer affects its rating. We then go on to look at some of the transformer devices that we use to make sure that the transformer is operating within its parameters. Transformer tap changers are used to alter the voltage on the network. In the next section, we will look at the main types of tap changers that we use, including no-load and on-load. In the final sections on transformers, we will look in detail at how we protect the transformer. In the first section, we will introduce the principles behind bias transformer differential protection. We will look at the bias curve to try and understand why it's required. In the final section on transformers, we will look at how we connect the current transformers for the various differential schemes that you will come across, and then complete the section by looking at how we pull all the transformer protections together. SCADA systems are critical to the operation of most transmission substations, and they are used to provide control and monitoring functions. We will look at the typical architecture behind a SCADA system and see how we connect all the primary plant and other systems to the LANs and RTUs that interface with a SCADA system. As you can see, we covered a lot of ground on this course. I would recommend that you take your time on each of the sections and make sure that you understand them fully before carrying on. You can easily rewind and replay any part if something isn't clear. I've also attached some questions at the end of each section, but if something doesn't make sense, please don't hesitate to contact me. The first section on the course comes next and covers DC systems. I hope you enjoy it. The circuit breaker is critical for clearing faults on the electrical system, but sometimes things go wrong. and the circuit breaker fails to clear the fault. In this section, we will look at how we detect this critical situation and what actions we need to take to ensure that the electrical system is protected from collapse. The aims of the course today are: introduce the principles of circuit breaker failure protection. Look at how circuit breaker failure protection operates. See what the impact of a circuit breaker failure has on the rest of the network. Very often, circuit breakers will sit in a closed position for many months without being operated. Although we can use the trip circuit supervision circuit to detect a fault in the DC supplies and wiring, an issue with the circuit breaker mechanism may result in it not opening when asked to do so. When a circuit breaker fails to operate, this is defined as a circuit breaker failure. This is the common symbol for a circuit breaker failure relay. For a distribution system, time is not that much of an issue, and any fault remaining on the system after the circuit breaker failure will eventually be cleared by other protections in the chain, operating their circuit breakers. On transmission systems, we don't have the luxury of being able to wait around for this to happen, so we provide a dedicated circuit breaker failure system for each circuit breaker on the network. This can be achieved by using discrete relays, or more normally in modern systems, by using inbuilt functions on the circuit breaker control relays. Here's a typical multifunction circuit breaker control relay. These are the conditions for a circuit breaker failure. The first thing is we must have a protection trip. If there's no fault, we can't have a circuit breaker failure condition. As soon as the protection trip happens, we start a time delay to allow time for the circuit breaker to open. We also monitor the current and see if it's flowing through the circuit breaker. If we get to the end of the time delay and current is still flowing through the circuit breaker, we have a circuit breaker failure, and we need to take immediate action. The key thing to remember is that we only declare the circuit breaker failure when a protection trip has been initiated and an actual fault has occurred on the network. If the circuit breaker fails to open when it is just being opened by the network operator, they will quickly see the issue, and will have plenty of time to switch other circuit breakers on and off to isolate the faulty circuit breaker. In a fault situation, immediate action is required when the circuit breaker fails to open, as we have fault current flowing, which is damaging the equipment and may cause a network-wide collapse. Firstly, let's see how the system works when the circuit breaker is operating normally. Here we have a typical feeder circuit with a circuit breaker and a current transformer feeding an overcurrent relay. We normally connect the circuit breaker failure relay to the same current transformers as the protection relay. Let's now monitor the time to show the sequence of the circuit breaker failure. Let's now close the circuit breaker. As soon as you close the circuit breaker, current will flow through the CT. The value of the current will depend on the load. Let's now apply fault on the feeder. Once the current gets above a certain threshold, the protection relay will energize the circuit breaker trip coil. After a short time delay, the circuit breaker mechanism will operate. The circuit breaker contacts will open, and eventually the current will stop flowing. After the short time delay, we reset the protection system, and the whole system goes back to its original state. This is the normal fault clearance sequence for a healthy circuit breaker, The amount of time from the moment of the protection trip to when the current stops flowing is classed as the clearance time. This is fairly constant and depends on the operation of the circuit breaker mechanism. The time from when the current stops flowing to when the protection system resets is called the overshoot time. Let's now see what happens if the circuit breaker fails to operate. Here's our standard feeder circuit from before. Let's now close the circuit breaker again. Let's now apply fault on the feeder. As before the current increases, the overcurrent relay detects the fault and sends a trip signal to the circuit breaker. But for some reason, the circuit breaker fails to operate. After the fixed time delay, the circuit breaker failure relay operates and initiates a circuit breaker failure. The time delay that we wait before declaring a circuit breaker failure consists of the clearance time and the overshoot time. A circuit breaker failure is a critical event on a network, as we have a fault on the system which is not being cleared, which may critically damage equipment and even cause a system-wide collapse. When the circuit breaker failure system operates, we have to immediately trip the other circuit breakers that are feeding the fault. We normally do this by using the tripping and communication facilities already provided by the other main system protections, for example busbar protection or feeder protection, to trip all of the circuit breakers connected to the failed breaker. Let's now see how a typical network reacts to a circuit breaker failure. Here we have a typical transmission network, with ends A, B, and C. Let's now add a breaker failure relay to all of the circuit breakers on the network. Let's now close all of the circuit breakers. Current now flows from end A through the feeders and onto ends B and C. Let's now add a fault on the feeder connecting ends A and C and see what should happen when the system is operating normally. As expected, the currents all now increase. The current NC now reverses direction and feeds the fault. The protection systems on breakers D and I trip, clearing the fault from the system. The rest of the currents in the network now reduce and the system goes back to normal. Let's now reset the system and see what happens when we have a circuit breaker failure. So here's our feeder fault as before. This time, circuit breakers D and I receive a protection trip signal, but only circuit breaker I operates. After a short time delay, the circuit breaker failure relay on breaker D now operates, initiating a circuit breaker failure condition. Because circuit breaker D has failed to open, fault current is still flowing around the network and is being fed in from end A and backfed from end B. The only way we can remove fault current now is to remove all the possible sources of the fault current. This is done by tripping breakers A, B and C. The fault has now been removed from the system, but as you can see, the whole network is now being disconnected. When the network is designed, it is pretty obvious which other circuit breakers need to be operated when a particular circuit breaker fails. Normally, this is all of the circuit breakers connected to it. To avoid having to set up dedicated systems and secondary circuits, we can normally initiate other protection systems, which will then trip the circuit breakers at the remote end feeders, or in the case of busbars, tripping all of the circuit breakers connected to a busbar using the busbar protection system. Each circuit breaker needs its own unique circuit breaker failure logic, which knows what action to take when that breaker fails to operate. When the circuit breaker failure system is initiated, we have to immediately trip the other circuit breakers that are feeding the fault. This normally means tripping all of the circuit breakers connected to the faulted circuit breaker. Let's do a worked example. For the scenario shown, work out which circuit breakers need to be tripped to clear the fault. Here we have the network from before, with a fault on the feeder connecting end A to end B. We have a circuit breaker failure initiation on circuit breaker E. Let's run through the full sequence and see what needs to happen. Firstly, let's see what happens if the network is operating normally. Let's now close the circuit breakers. A fault has appeared on the feeder connecting end A and end B. As before, all of the fault currents will increase, with current backfeeding from ends B and C. If everything is operating normally, breakers B, E and G are all tripped by their protection systems, clearing the fault. The rest of the network now returns to normal. Let's now see what happens when we have a circuit breaker failure on circuit breaker E. Breakers B and G have already tripped, so those systems have already been isolated from the fault, but we are still getting a current backfeed on end B. The only solution to this problem is to trip circuit breaker F, clearing the fault. When a circuit breaker failure is detected on breaker E, it will send a trip signal to all of the circuit breakers electrically connected to it, namely breakers B, F and G. If a circuit breaker has already been tripped by the protection system and already open, that's fine. Their circuit breakers just won't react. Circuit breaker fail protection is a pretty blunt weapon to use, as it doesn't care if every customer on the network is disconnected by its actions. It will trip the circuit breakers that it is programmed to trip, regardless of the consequences. So we need to be sure that a circuit breaker failure has actually occurred before taking any action. This is why we have the insurance of the overshoot timer. Let's now summarize what we've learned today. A circuit breaker failure system is provided on transmission system circuit breakers to deal with the failure of any circuit breaker under fault conditions. When a circuit breaker does fail after the fault is detected, all of the circuit breakers connected to it need to be tripped to clear the fault current. The circuit breaker failure relay operating time consists of the circuit breaker clearance time and an overshoot time to ensure that the circuit breaker has actually failed. Congratulations for completing this section. You should now understand how circuit breaker failure protection detects that something has gone wrong with the system and takes action to clear the fault from the system. I have attached some questions on today's section to test your knowledge. Most substations use DC to supply the protection and control systems so that when the AC supply fails, we can continue to monitor and control the network. In this section, we will look at all of the DC systems that you will come across inside a typical transmission level substation. By the end of this section, you will know the basic architecture of a DC system, understand how the batteries are sized and operated, and how the DC system is protected from earth faults. The aims of the course today are: look at how we use DC systems inside substations. See how we connect the battery and charger systems together. Learn what criteria we use to size the batteries. See how we use battery grounding to detect a fault. Although substations control the flow of AC power, the protection and control systems are mainly powered by DC. When the substation is operating normally, the DC supply to the protection and control systems is fed via AC to DC converters, with the AC coming from the main network. When the supply from the AC network gets disconnected, due to switching, or a fault on the network, battery systems are used to maintain the DC supply. Most substations use a 110 volt DC system voltage, with a 48 volts DC system used for the SCADA and telecom systems. Let's look at a typical 110 volt DC system. Firstly, we have the main AC supply from the substation system. This is normally derived from the main network via the substation service transformers. We then convert the AC supply to a DC output using an AC to DC converter. The DC supply is then fed to the DC distribution system, which distributes the DC power to all of the equipment within the substation. In case the AC system fails, we have a backup substation battery. Under normal conditions, the battery will be charged by the AC to DC converter. The AC to DC converter therefore needs to be rated for the full DC system load and the charging current necessary for the battery. The battery itself also has to be rated for the full DC system load whilst the AC system is disconnected. For most HV substations, the battery is designed to supply the full substation DC load for up to 12 hours after the failure of the AC supply. We like redundancy, so we supply two separate battery and charger systems. These feed their own busbar and loads. The normal configuration is for each converter battery system to feed its own busbar. In the event of one charger battery system failing, the other system is fully rated to feed the full substation DC load via the link between the busbars. The battery sizes required to maintain the DC supplies are substantial in transmission substations. To achieve the rating, numerous lower voltage battery cells are connected together. Here's a typical battery cell. The individual cells tend to be rated at 1.8 volts or 2 volts each. We therefore connect sufficient cells in series to get the required system voltage. The cells also have an ampere-hour rating, which is the amount of energy that they can store. If we required a 50 volt battery and the individual cell voltage is 2 volts, we would simply connect 25 cells in series. If the arrangement does not meet the ampere-hour rating required, we can connect additional battery banks in parallel. Here we have a typical battery rack for the transmission substation. Firstly, we have the individual cells. Because of the quantity of cells required, these are usually stacked in multi-tiered racks. We normally use plastic-coated metal support racks. These are resistant to any acid that may leak from the batteries. Here's a view of the interconnections between the cells. The cells are connected in series using metal links, with the positive terminal of one cell connected to the negative terminal of the next. On each individual cell, you will see the cell voltage, the ampere-hour rating, and the specification. All the cells are individually numbered. This is used for maintenance purposes. Where we are using lead-acid batteries, we have a vent or hole for topping up the acid. The main issue with batteries is that their output voltage is not constant as the battery discharges, but instead follows a discharge curve. A typical discharge curve is shown below. The curve has three distinct stages. When the cell is first connected to the load, there is a high rate of voltage drop. Depending on the load applied, this initial phase can last from a few minutes up to an hour. Eventually, the rate of the voltage drop stabilizes and the battery slowly discharges. The final phase is when the battery is reaching the end of its capacity. In a similar way to the initial period, the rate of voltage decline increases substantially. As you would expect, if the current drawn by the load increases, the rate of the voltage drop also increases, and the battery runs out of capacity quicker. Here we have a discharge curve when the current drawn by the load is 1 amps. If we now increase the load current, the voltage drops at a faster rate and the battery discharges quicker. This decline continues as the load current increases. To size a battery, we therefore need to know the current drawn by the system, how long we want the battery to supply the load for, and the minimum voltage required at the end of the load cycle. This is the standard discharge curve that you will see for most types of battery, either nickel-cadmium or lead-acid types. The key factor in how quickly the battery discharges is obviously the load that we apply to it. The higher the load, the more current is drawn from the battery, and the faster it will discharge. When the battery voltage has reached a level when it can no longer operate the equipment, it becomes useless, so the battery sizing calculation has to take this minimum voltage into account. The typical loads that may be applied on a HV substation after the main AC supply has failed and the DC battery is supplying the load can be broken down into two main elements: standing loads and dynamic loads. Let's look first at standing loads. These are the loads that are continuously drawing power from the system and include protection relays and systems. Even when there's no faults, protection relays still draw current from the system. SCADA and control equipment. Indication equipment such as annunciators. And finally measuring equipment such as transducers. Next we have dynamic loads. These are events that happen through the course of the discharge cycle. They are harder to predict, so we use our knowledge of the system to assume what might happen. These include circuit breakers or other primary plant open and closing. Mechanisms, spring charge motors recharging. These can draw a substantial amount of current from the DC system. Here is a typical load cycle for a HV substation. This is a likely sequence of events that may happen after the main AC supply has failed, and we are now relying on the DC batteries to supply power to the equipment. Firstly, let's create a graph with current in amps on the left-hand side and time in hours across the bottom. The first thing to add is the standing load. This is a fixed amount of current for the full duration of the battery discharge cycle. To calculate the standing load, we simply add up all the protection, SCADA, indication, and control loads on the system. In this case, we've made the standing load 82 amps. Next, we add the dynamic loads. In the first case, we've calculated the load for all the circuit breakers tripping on the system, and assumed a load current of 142 amps for 1 second. Following the circuit breakers tripping, we've assumed that all their spring charge motors recharge, with a value of 102 amps for 4 seconds. Next, we've assumed that after a few hours, we close 30% of all the circuit breakers, and this event is repeated throughout the cycle. Finally, we want to make sure that there's enough energy left in the battery to trip all of the circuit breakers on the system, so we add this load right at the end of the cycle, The standing load is fairly easy to calculate and is the main factor in sizing the battery. The estimate should be fairly accurate, as we are simply adding up all of the equipment loads, all of which are well known. This estimated value can then be checked by measuring the actual load current drawn by the DC system after the substation is energized. The dynamic loads are a bit trickier to estimate, but by using our knowledge of what happens to the system when the substation is disconnected from the network, we can come up with a reasonable assumption. The current and time information from the load cycle is fed into a software program supplied by the battery manufacturer, together with the required battery output voltage at the end of the load cycle. The software will then indicate the ampere-hour size of battery required for the application. It is normal practice to add a sizable percentage onto the calculated ampere-hour rating to allow for future expansion of the substation, for any unexpected events during the load cycle, and the aging of the battery over time, which will reduce its available ampere-hour capacity. A figure of 50% of calculated battery rating is not unusual. To allow us to detect a ground fault on the 110-volt DC system, we normally use center point grounding. Here's a typical battery and load configuration. Here is the ground detector connected to the center point of the battery. We provide a high-value resistor in series with a ground fault detector to limit the fault current to milliamps should a ground fault occur. The ground fault meter is simply a milliammeter, which detects the flow and direction of the current. During normal operation, the current flows from the positive side of the battery through the load and back to the negative side of the battery. Should a fault occur on the positive terminal, some current will start flowing through the ground detector, and back to the center point of the battery. Only a few milliamps will flow because of the resistor in series with a ground connection. The ground fault detector will detect the flow of current and indicates a fault on the positive terminal. For a fault on the negative terminal, the current will flow in the opposite direction, and the ground fault meter will indicate a fault on the negative terminal. Having this type of earth fault detector is a good way of monitoring the health of the DC system. For major battery earth faults, the fault current generated should be sufficient to operate the MCBs immediately. The earth fault monitor will also trip the circuit breaker. For minor earth faults, an alarm will be generated and the battery left connected. The engineer can then trace and repair the fault at a later date. It is quite common for older substations to have a number of minor battery earth fault alarms caused by the insulation on the cables and equipments failing as they age. These will be very difficult to trace, and many may be left in place until the DC system is fully overhauled. The battery chargers have to be rated for a DC output large enough to supply the full substation DC load and to charge the battery during float and boost charging. Float charging is when the system is acting normally and we are gradually topping up any energy lost from the battery. The float charge voltage is typically 10% above the standard battery cell voltage. Boost charging occurs when the battery has been heavily discharged and we need it to be operational quickly. To achieve this, the boost charge voltage is increased to a voltage typically 20% above the standard battery cell voltage. Let's summarize what we've learned today. Substation DC systems have two independent charger battery systems to provide a main and backup DC supply when the main supply is lost. To size the battery, we need to know the load cycle and the required minimum battery voltage at the end of the cycle. Most 110-volt DC substation batteries are center point grounded, so that a ground fault can be detected on either the positive or negative circuits. Congratulations for completing this section. You should now have a clear picture of how the substation DC system operates and understand why it is so critical to the operation of the electrical system. This is an important topic, and understanding it is essential to the subject matter in the next section, so please go back and redo the sections that didn't make sense. I've attached some questions on today's section to test your knowledge. In this section, we will look at circuit breaker protection. Circuit breakers are a critical device in the electrical network, as they switch power around the system and operate quickly and securely to clear any fault on the system as they occur. By the end of this section, you will understand all about circuit breaker auxiliary switches and know what protection systems we use to ensure that the circuit breaker is operating as it should. The aims of the course today are to introduce the principle of tripped circuit supervision, to show how single-phase circuit breakers are operated, to introduce phases not together protection, circuit breaker auxiliary switches are critical to the operation of the protection systems. The most common types that we use are normally open, sometimes labelled as NO. These are open when the circuit breaker is open. They're sometimes labelled as A contacts. Next we have normally closed, sometimes labelled as NC. These are closed when the circuit breaker is open. They're sometimes labelled as B contacts. Here we have two typical circuit breaker contacts, and the normally closed circuit breaker auxiliary switch, and the normally open circuit breaker auxiliary switch. To see what's happening, let's connect the auxiliary switches through a supply to some bulbs. As the circuit breaker contacts are in the open position, the normally closed contacts are closed, and the bulb connected to the B contact is lit. Let's now close the circuit breaker contacts and see how each of the circuit breaker auxiliary switches behaves. As the circuit breaker contacts move from the fully open position, the normally closed auxiliary switch opens, removing the supply to the bulb. Once the circuit breaker contacts gets to the fully closed position, the normally open auxiliary switch closes, lighting the bulb. As we can see, there's quite a large gap between the normally closed and normally open circuit breaker auxiliary switches. For most circuits, this gap is essential, as we need to know whether the circuit breaker is definitely open or definitely closed. We don't want an intermediate state. Let's now open the circuit breaker. As we can see, the circuit breaker auxiliary switches change state in line with the circuit breaker contacts. When we are switching current transformer wiring, this gap can cause issues, as we cannot open circuit as CT. This would happen when we went from CB open to CB closed status. For these circuits, we provide other types of auxiliary switches. Normally closed at late break are normally open early make. Let's now close the circuit breaker again and see what difference it makes. We can see clearly that the normally closed late break stays closed for much longer than the normally closed auxiliary switch. When we get to the midpoint of the circuit breaker, we can see clearly that both of the new auxiliary switches are connected. This stops us open circuiting the current transformer wiring. You will come across many types of circuit breaker auxiliary switches, including early and late break, and early and late make. Some protection and control devices need to know that the circuit breaker is definitely in the open or closed position, while other systems need to know when the circuit breaker is moving. Having the different types of circuit breaker auxiliary switches allows us to provide the correct information. The trip circuit is critical to the operation of the substation, as we need to be certain that when the protection detects a fault, the circuit breaker will be ready to open and clear it from the system. One way we ensure this is to have trip circuit supervision. Trip circuit supervision ensures that the trip circuit is healthy by monitoring the DC supply and all of the trip wiring. If it fails or a connection comes loose, it will operate and let the control center know that the circuit breaker cannot be opened. We monitor the supply whilst the circuit breaker is closed, but also when it is open, as we do not want to close a circuit breaker if it is not possible to open it. Here we have a typical trip circuit for the circuit breaker. The trip circuit supervision is connected as follows. Firstly, we have an A coil monitoring the trip contacts. This coil has a high resistance. We daisy chain the trip wiring and put the A coil right at the end of the chain, so that it monitors 100% of the wiring. As we said previously, we also want to monitor the trip circuit when the circuit breaker is open. To do that, we provide a B coil. We then feed contacts from both the A and B coils into a third coil, the C coil, which is connected to its own DC supply. Let's now close the circuit breaker and see what happens. In this position, the A coil is energized, and current is presently flowing from the positive supply through the A coil, through the circuit breaker auxiliary switch, the trip coil, and onto the negative supply. Because the A coil has a high resistance, there is insufficient current to operate the trip coil. As we can see, the A coil is now keeping the C coil energized, indicating that the trip circuit is healthy. If the supply drops off, or we have a break in the wiring, the A coil will drop off, de-energizing the C coil and initiating a trip circuit faulty alarm. Let's now remove the fault and reset the relay. If any of the trip contacts initiate, the A coil will drop off, and there will be a short time delay before the B coil energizes. For this reason, the C coil has to have a short time delay to deal with the gap between the A coil de-energizing and the B coil energizing. In the open position, current passes from the positive terminal through the A and B coils, through the trip coil, and onto the negative terminal. Again, because the A and B coils have such a high resistance, the current is insufficient to operate the trip coil. Trip circuit supervision is a great way of monitoring the health of the trip circuit, and very often provides an indication of problems that have arisen elsewhere in the substation, either when the DC supplies have failed, or when someone's left a control link out on a panel in the control room. When a trip circuit supervision is received, the operators in the control room will take immediate action. Depending on the electrical utilities policy, the network may be reconfigured to take the affected circuit breaker off the network until the issue is rectified, as it can no longer be relied upon to clear any faults that may occur. Most circuit breakers are three-phase units, where the red, yellow, and blue phase circuit breaker contacts are all operated by the same operating mechanism. Here's a typical three-phase circuit breaker. We just have one set of trip and close signals that operate the circuit breaker mechanism. At transmission levels above 230 kV, we tend to have single-phase circuit breakers. Therefore, we have a single-phase circuit breaker with its own mechanism on the red phase, yellow phase, and blue phase. For single-phase circuit breakers, we simply duplicate all of the push-button, switch, and relay contacts and feed them separately into each of the circuit breaker phase mechanisms via a common circuit breaker marshalling kiosk. Keeping the three-phase trip and close circuits electrically separate allows us to trip and close the circuit breaker phases individually. One thing we need to check when using single-phase circuit breakers is to ensure that all three circuit breakers operate at the same time. To check this, we use Phases Not Together protection. This protection monitors the red phase, yellow phase, and blue phase circuit breakers and initiates an alarm when they do not all operate within a fixed time. This is the common Phases Not Together circuit that we use. We have parallel chains of normally open auxiliary switches in series with a parallel chain of normally closed circuit breaker auxiliary switches, connected to a timer which is used as a Phases Not Together relay. We normally set the timer to a setting of 50 milliseconds to allow for contact bounce and the time gap between the normally open and normally closed auxiliary switches. In the healthy state when the breaker is open, there is no positive feed to the relay and it therefore doesn't operate. Let's now close the circuit breaker. In the closed position, when everything's healthy, there is still no feed to the Phases Not Together timer. Let's now open the circuit breaker. Let's now simulate something going wrong and not close the blue phase circuit breaker. As we can see, we now have a path onto the Phases Not Together timer. It operates, indicating that something's gone wrong. A Phases Not Together fault normally occurs due to a mechanical failure of the circuit breaker mechanism on one of the circuit breaker phases. The Phases Not Together protection will detect that one of the circuit breaker phases fails to operate or operates later than the other circuit breakers. Both of these conditions will cause a serious issue on the loads on the three-phase network. The faulty circuit breaker will normally be taken out of service by the control room operator until the affected circuit breaker is repaired. Let's now summarize what we've learned today. Circuit breaker trip circuits are key to the operation of the protection system and are monitored using trip circuit supervision protection. We use single-phase circuit breakers on high-voltage circuits and feed all of the trip and close signals into each individual breaker mechanism. Phases Not Together protection is used to ensure that all three single-phase circuit breakers are operating together. Congratulations for completing this section. You should now know the different types of auxiliary switches that we use, how we ensure that the trip circuit is operating normally, and how we ensure that the circuit breaker is operating correctly. This is an important topic, and understanding it is essential for the subject matter in the next section, so please go back and redo the sections that didn't make sense. I have attached some questions on today's section to test your knowledge. When a fault occurs on the system, we trip the circuit breaker, then clear it. For certain types of faults on electrical systems, we sometimes want to re-close the circuit breaker to get the customers connected again. This principle is called auto-reclosure, and in this section, we'll see how this can be achieved safely and in a controlled way. By the end of this section, you will understand the sequence of events that occur during a fault, and see how timers are used to auto-reclose the circuit breaker to ensure that the customers are reconnected as quickly as possible. The aims of the course today are: introduce the principles of circuit breaker auto-reclosure, identify the difference between transient and permanent faults, look at how circuit breaker auto-reclosure operates, some faults on the network are permanent and don't go away with time. These types of faults need to be permanently disconnected to avoid further damage and the collapse of the system voltage. On some parts of the network, we may have transient faults. Here's a typical overhead line with a tree underneath. If the tree grows, the branches of the tree may touch the overhead line. The protection system will then detect a fault and trip the circuit breaker. Very often the current flowing into the tree results in the tree branches burning and falling off, and the fault is cleared. The system can therefore be restored. Other typical transient faults include tracking on insulators caused by ice or snow, birds or animals touching an overhead line, lightning strikes, two conductors on an overhead line touching due to the wind. Identifying the difference between a transient and permanent fault is not always easy, as they will both create the same level of fault current and operate the protection systems. In the example of a tree touching the line, it could develop into either type of fault, depending on the size of the branch, how it's fallen onto the line, and how much current is fed into it when the fault occurs. Some countries have major issues with animals, such as monkeys touching the line. Again, the monkey could die and fall off the line once it's electrocuted, or fall onto the line, causing a permanent fault. This is the common symbol for a circuit breaker auto-reclosure relay. On a distribution system, circuit breaker auto-reclosers tend to be integrated into the switchgear itself. These can be mounted on the overhead line poles or inside the distribution substation. Auto-reclosure equipment were first installed out of necessity on distribution power lines, as trees and animals regularly touch the live line, tripping the protection system and disconnecting the customers. When the line engineer arrived at the fault, they often found that the fault had cleared itself, as the tree branch had burned off, or the animal had died and fallen to the ground. Auto-reclosure provides a solution to this problem by allowing the circuit breakers to reclose after the fault to see if it's been cleared. If it has, the system is restored at no cost to the network, and the customers have had minimal disruption. If a fault is still present after reclosure, the system locks out and an engineer is dispatched to resolve the issue. For the transmission system, auto-reclosing functions are either built into the main feeder protection relays, or alternatively use discrete relays. The auto-reclose relay normally uses the same CTs as the protection system to detect the flow of current. Here's some typical discrete auto-reclose relays. We only use auto-reclosure on parts of the network where we know transient faults are possible. These tend to be circuits containing overhead lines or outdoor equipment. On a typical overhead line, 80% of the faults are transient in nature. We never auto-reclose circuits when a fault has been detected on power cables or on key plants such as transformers, as applying fault current to these equipments for a second time may cause irreparable damage. Let's look at the sequence of a typical auto-reclose relay for a transient fault. Here's a typical feeder circuit. As we said previously, the auto-reclose relay normally uses the same current transformers as the protection system. Let's now close the circuit breaker. As soon as the circuit breaker closes, the current on the feeder will increase. Let's now simulate a transient fault on the feeder. The current will now increase due to the fault, and the protection relay will pick up. We start the auto-reclose sequence. The circuit breaker is now tripped, and the circuit breaker contacts open. The current now reduces, and after a short time delay, the arc will be extinguished. After a fixed time, we reset the protection system automatically. We then try and reclose the circuit breaker. Once the circuit breaker is closed, the current starts flowing again. The duration of the time from when the arc was extinguished to when the current starts flowing again is when the circuit was dead. We therefore identify this as the dead time, and is effectively the time from when the circuit breaker contacts open to when they close again. This is a known factor for most circuit breakers, and depends on the circuit breaker design and the type of mechanism. After the current starts flowing again, and we don't detect any further faults, we reset the auto-reclose system, and it goes back to its original state. The difference in time between when the current starts flowing and the system resets is called the reclaim time. This is the time during which we check to make sure the system is healthy. Both the dead time and the reclaim time are adjustable settings that we can apply to the auto-reclose system. Let's now look at what happens for a permanent fault. Let's now close the circuit breaker. This time the tree is falling onto the line and isn't going anywhere. Again, the current increases, the protection system detects the fault and initiates the auto-reclose sequence. The breaker trips. The circuit breaker contacts open, and the arc is extinguished. After a short time delay, the protection resets. The auto-reclose system now tries to reclose the circuit breaker. But this time, because the fault has not been cleared, the protection system detects the fault and straight away opens the circuit breaker, and the arc is extinguished. Because the fault was still present after we reclosed the circuit breaker, we now lock out the auto-reclose system. If a fault has been detected after the circuit breaker has been reclosed, we do not reset the protection system. This prevents the circuit breaker from trying to reclose again. We then lock out the auto-reclose scheme until the engineer has visited the fault location and cleared it from the system. This is called a single reshot auto-reclose scheme, as we try only once to reclose the circuit breaker. When we are looking at the auto-reclose sequence, we therefore need to consider two main time delay settings. The first one is the dead time. This is effectively the time that we wait before we try and close the circuit breaker again after a fault. This time depends on the system requirements, i.e., how long we can allow the system to be offline before our customers start having issues, and our knowledge of what's likely to cause the transient faults. For example, if trees are causing the issue, do we need to allow time for them to burn off? For a distribution system, we can make the dead time as slow as 1 or 2 seconds. For a transmission system, the time might be less than 100 milliseconds, as the system may collapse if we don't connect any quicker. The next time is the reclaim time. This is effectively the time that we set after we close the circuit breaker, whilst we wait to see if the fault has been cleared. For systems where we only try and reclose once, i.e. single reshot auto-reclosing, the auto-reclose system will lock out and stop the breaker closing until the fault has been investigated. In some distribution systems, we know the main faults are due to animals or vegetation, and we use multi-shot auto-reclose systems that try more than once to close the circuit breaker. The number of shots could be set on the relay. When we are assessing the dead timers and reclaim timers, we are balancing the needs of the customers and the network and the integrity of the equipment. The customers obviously want a minimal outage time as it disrupts their operations. The electrical utilities are also incentivized to reduce the duration and frequency of any outages, as very often they are financially penalized every time a customer is disconnected. Balanced with this is the need to protect the integrity of the equipment. Repeatedly closing equipment onto a fault may cause permanent damage to the equipment and will certainly lead to increased maintenance times further down the line. So we need to quickly identify the difference between a permanent and a transient fault. Let's summarize what we've learned today. Auto-reclose systems are used when we want to reclose circuit breakers after a fault has occurred. When the auto-reclose system is closed onto a permanent fault, it locks out after the set number of tries. The dead time of the auto-reclose system is the time delay before the circuit breaker is closed after a fault occurs. The reclaim time of the auto-reclose system is the time period during which we see if the fault has been cleared or not. Congratulations for completing this section. You should now be familiar with circuit breaker auto-reclosure schemes and understand how useful they are in reconnecting customers after a transient fault has occurred on the system. I've attached some questions on today's section to test your knowledge. Congratulations for making it halfway through the course. When we close circuit breakers, we have to ensure that the two systems that we are connecting together have similar parameters, otherwise the circuit breaker may get damaged. To do this, we use synchronizing equipment. By the end of this section, you will understand all of the parameters we need to check before closing a circuit breaker, and what equipment and circuits we use to ensure that the circuit breaker is closed safely. The aims of the course today are: introduce the principles behind electrical synchronizing, show what parameters need to be in line to allow us to synchronize two electrical networks, look at how we obtain the voltages that we need to allow synchronization to take place. In every network, the voltages are continuously varying as the loads and network configurations change. Here we have two networks A and B. As we can see, the red, yellow and blue phase voltages are continually changing. If we now try and close the circuit breaker connecting these two networks, the difference in these voltages may cause significant damage to the circuit breaker. We therefore check the following parameters of networks A and B before closing the circuit breaker that connects them together: the voltage, frequency, and phase angle. We call this procedure synchronizing. This is the common symbol that we use for a synchronizing relay. Most modern substations have automatic synchronizing equipment and manual synchronizing equipment. Here's a typical synchronizing relay. We call the relays that synchronize automatically check synchronizing relays. Check synchronizing relays are used when we are trying to close the circuit remotely, either from the main network control center or from the substation control room PC. When the remote close signal is issued, the check synchronizing relay checks the voltage, frequency and phase angle for networks A and B. If they are within the tolerances set inside the relay, a close signal will be sent to the circuit breaker. We also provide manual synchronizing equipment in the substation control room so that the engineers can close the circuit breakers locally. To allow them to do this, we provide a frequency meter which shows the frequency on both networks, a voltmeter that shows the voltage on both networks, and a synchroscope that shows the phase angle difference between the two networks. The operator watches all three meters carefully, and when they think they're close enough, they manually close the circuit breaker. Manual synchronizing is normally used as a backup when networks are difficult to synchronize or the check-sync relays are out of action. Using synchroscopes and manual synchronizing equipment takes a trained eye, as the three parameters can all be moving at different speeds. In most cases, you will find that the frequency and voltage of the two networks are about the same, and the tricky one to match is the phase angle. If the operator doesn't get it quite right, a loud bang will be heard from the circuit breaker as it closes, as power flows across the contacts. Let's now add the sync check contacts into a typical circuit breaker closed circuit. If the operator is doing a local close, they will operate the local close switch manually when the 3 meters show that it is safe to do so. Let's now reset the system. For a remote close, the circuit breaker will close when the remote signal is given and the check sync relay closes to indicate the systems are now in sync. The voltages that we use to synchronize the circuit breaker are taken from the system voltage transformers. We can either compare the phase to neutral voltages of the two systems being connected, or the phase to phase voltages. On transmission systems, we tend to compare the phase to phase voltages, as they contain more information. Here's a typical transmission network. In this system, we're comparing the red and yellow phase voltages. We tend to call the voltage of the network we want to connect to the running voltage, and the voltage of the network we are trying to connect from the incoming voltage. Where one or both of the networks are dead, i.e. no voltage, the check sync relay will close the circuit breaker immediately. It is normal to provide a synchronizing relay either per circuit breaker or sometimes a common relay per bus bar. It is essential that these relays are fed the correct running volts and incoming volts. The problem is, any circuit breaker on the system can be in the open or closed position, and we cannot parallel VT secondary circuits, so it can be difficult to work out what the running volts and incoming volts are for any particular circuit configuration. Let's look at a typical transmission substation. Let's energize the network by trying to close circuit breaker A. The incoming volts for the check sync relay will come from the voltage transformer on incoming A. We get the running volts from the voltage transformer on bus bar number 1. Because the incoming is live and the bus bar is dead, the check sync relay will close the circuit breaker immediately. Bus bar number 1 is now energized. Let's now try and close the circuit breaker on feeder D. In this case, the incoming volts is derived from the voltage transformer on feeder D. Again, we take the running volts from the voltage transformer on bus bar number 1. As the feeder is presently dead, the check sync relay will close the circuit breaker straight away. Let's now close the circuit breaker on incomer B. we take the incoming volts from the voltage transformer on incomer B, and the running volts from the voltage transformer on busbar number 2. Again, because the busbar is presently dead, the check sync relay will close the circuit breaker immediately. Let's now close circuit breaker C. Try and guess which voltage transformers we need to use, and which will be the incoming and which will be the running volts. To be fair, which way round we have the incoming volts and running volts doesn't matter. In this case, we take the incoming volts from the voltage transformer on busbar number 1, and the running volts from the voltage transformer on busbar number 2. This time we're connecting 2 live circuits, so the check sync relay will not close until the voltage, frequency and phase angle are within the settings defined by the check sync relay. In this case they appear to be, and the check sync relay closes circuit breaker C. We use a voltage selection circuit, which mimics the network that we are going to synchronize and uses the circuit breaker auxiliary switches to ensure that we don't parallel any voltage transformers. The first thing that we do is create a red phase running bus and a blue phase running bus. These will connect all of the VTs together. As we've seen in the previous circuit, the busbar voltage transformers always provide the running voltage for all of the check sync relays. Let's now connect the busbar 1 voltage transformer to the running bus. Let's now connect the busbar 2 voltage transformer to the running bus. As we said previously, we cannot parallel voltage transformers. So what we do is, we use the auxiliary switches from circuit breaker C to separate the circuit. When circuit breaker C is open, each voltage transformer feeds its own busbar. When circuit breaker C is closed, we prioritize one of the voltage transformer supplies and disconnect the other. In this case, we prioritize the voltage transformer for busbar number 1. Let's now add the check sync relay for feeder D. The incoming volts is fed from the voltage transformer on its own feeder. We then take the running volts from the red phase and blue phase running buses. We repeat this connection for all the other circuits on busbar number 1. We then connect all the circuits connected to busbar number 2 onto the running buses for number 2. Let's now add a sync check relay for breaker C. Breaker C gets one set of running volts from the running buses from busbar number 1 and the other set of running volts from the running buses for busbar number 2. Voltage selection circuits in old complex substations can be a nightmare to commission due to the large number of inputs involved. To implement the scheme, we need to make connections to every single circuit breaker mechanism to pick up the auxiliary switches and every single voltage transformer to pick up the secondary voltages. They are also notoriously difficult to modify should we want to change the substation configuration, as every substation seems to have its own way of making the interconnections. Let's summarize what we've learned today. Before the circuit breaker connecting 2 networks can be synchronized, we need to check that the frequency, voltage level, and phase angle are all within tolerance. Most circuit breakers have a check sync relay for remote closure of the circuit breaker. Manual synchronizing equipment is also provided for closing the circuit breaker locally. Obtaining the running and incoming voltages that we need for the synchronizing equipment needs a voltage selection circuit, so that we don't parallel the voltage transformer secondary circuits. Congratulations for completing this section. You should now understand what parameters we check before we synchronize a circuit breaker, and appreciate how important it is to derive the correct running and incoming voltages to feed into the synchronizing relay. I have attached some questions on today's section to test your knowledge. Transformers are one of the most expensive devices that we use on the electrical network, and looking after them is one of the main goals when we design a protection system. This is the first of 4 sections associated with transformers on this course, and we start by looking at some of the basic design features of transformers. By the end of this section, you will understand all about transformer winding types and vector groups. The aims of the course are to look at the different ways that 3-phase transformer windings can be connected, to see how we use the different winding types on generator, distribution and transmission transformers, to introduce the idea of vector groups and see how they affect the phase shift. Double wound transformers consist of 2 electrically separate windings connected via a magnetic link. On the primary winding, we have primary voltage Vp and primary current Ip. On the secondary winding, we have secondary voltage Vs and secondary current Is. The magnetic core ensures that the lines of magnetic flux circulate evenly between the phases and increases the efficiency of the transformer. Transformer 3-phase windings can be configured in many ways. The main 2 arrangements are star connections and delta connections. Let's look at star connections first. The red, yellow and blue windings are positioned 120 degrees apart and connected at a common point called a star point. In most transmission and distribution systems, we normally ground the star point to provide a 0 reference point for the transformer and a path back to the transformer for any fault current. This is the symbol for a star-connected winding. Or, on the transformer symbol itself, we use the capital Y for the primary winding and the lowercase y for the secondary winding. We normally use star-connected windings on networks where we need a neutral connection, i.e. TPN systems. The other option is delta-connected windings. Here, the red, yellow and blue windings are all connected in series. This is the symbol we normally use for the delta-connected winding. Or, on the transformer symbol itself, we use a capital D for the primary winding and a lowercase d for the secondary winding. We normally use delta-connected windings on networks where we don't need a neutral connection, i.e. TP systems. When we design a double wound transformer, we can have any combination of star and delta windings that we require. Here's a star-star transformer, with a star winding on the primary and a star winding on the secondary. A star-star transformer traditionally has a 0 degrees phase shift. Let's see what that means. A 0 degrees phase shift means that the voltages on the primary and secondary windings are both in phase, and there's been no phase shift from the primary to the secondary winding. A simple way to show the phase shift across the transformer is a clock face, with 0 degrees at the top. We then show the phase shift in 30-degree increments. 11 o'clock will be plus 30 degrees. As we can see, the voltage on the secondary is now 30 degrees in advance of the voltage on the primary. Going the other way now, 1 o'clock will be minus 30 degrees, which means that the voltage on the secondary winding is 30 degrees behind the voltage on the primary winding. If we want to represent the transformer as a symbol, we call it a Y0, where the capital Y represents a star primary winding, the lowercase y represents a star secondary winding, and the 0 represents a 0 degrees phase shift. Let's now look at a delta-delta transformer. Again, a delta-delta transformer normally has a 0 degrees phase shift, and the clock faces are therefore the same as the previous transformer. We represent the delta-delta transformer as a D-D0. Let's now look at a delta-star transformer. Because of the physical arrangement of a delta-star transformer and the way the vectors are arranged, we naturally get a plus 30 degrees phase shift as we go from the primary to the secondary winding, as shown on this diagram. If we show the delta winding, then superimpose the star winding over the top and measure the phase angle, we'll see the difference is 30 degrees. Therefore, on the clock faces, the secondary winding is shown at 11 o'clock. This is represented in the symbol, which is a DY11. Let's now look at a star-delta transformer. Again, because of the physical arrangement, a star-delta transformer also has a 30 degrees phase shift, but in the other direction. The clock faces represent this, with the secondary winding now showing 1 o'clock. It's classed as a YD1 transformer. Designers take this phase shift into account when they design the electrical network to ensure that the voltages that appear at each voltage level in their network always have the same phase angle, as trying to join two networks with a 30 degrees phase shift would be blocked by the synchronizing relay on the circuit breaker. Having star and delta windings gives us some flexibility when we are configuring the network. Let's look at some typical uses. Here we have a transformer connecting a generator to a transmission network. Let's look at both of the systems. From the generator to the transformer, we have a TP or three-phase system with just a red, yellow and blue. From the transformer to the transmission network, we also have a TP system. For the generator side, we have a delta winding, which provides an efficient transfer of power and limits harmful harmonics. For connecting the transformer to a transmission network, we don't need a neutral, so we also provide a delta winding. The transformer is therefore a DD0 transformer. Let's now look at a different configuration, where we have a transformer connecting a generator to a distribution network. Again, the generator has a TP system, and therefore we use a delta winding on the primary. The distribution network is a TPN system, or three-phase and neutral system. We need a neutral conductor to generate phase voltages, so we provide a star winding. The transformer is therefore a DY11. Having a phase shift on transformers adds no economic value to the utility, and if all the transformers on the network were star-star or delta-delta, we wouldn't even be considering the phase shift. Unfortunately, we want to have TP systems on the generation and transmission systems to get rid of the neutral and save some money. And we need TPN systems on the distribution networks as we need a phase voltage. So at some point we have delta-star transformers and the natural 30 degrees phase shift that comes with them. Let's do a worked example. For the network shown, identify whether the transformer windings are likely to be star or delta connected, and what the phase shift will be from the generator through to the distribution network. Let's first identify where we have TP and where we have TPN systems. The generator is a TP system. The transmission network is also a TP system, and the distribution network is a TPN system. Therefore, for the transformer connecting the generator to the transmission network, we need delta windings on both the primary and the secondary. It's therefore a D-D0 transformer with no phase shift. For the transformer connecting the transmission network to the distribution network, we need a delta winding on the primary for the transmission network. On the secondary, it's a TPN system, so therefore we need a star winding. The transformer is a DY11 with a plus 30 degrees phase shift. If we look at the phase shift all the way through from the generator to the distribution network, we have a plus 30 degrees phase shift from start to finish. The angles shown for the star-star and delta-delta transformers have been considered as zero, which is what would happen if the windings are connected in their normal physical orientation. In practice, we can design transformers with any phase angle by changing the way that the windings are orientated inside the transformer. We have to be careful with transformer phase shifts, as connecting two networks together where the phase angles are different will result in damage to the circuit breaker. This is why we always measure the phase angle as one of our synchronizing parameters before we attempt to close a circuit breaker. The phase angle across a transformer also needs to be considered when designing transformer protection systems. We will look at the implications of this later in the course. Let's summarize what we've learned today. The two main ways to connect three-phase windings are the delta connection and the star connection. The way that we connect the windings affects the phase shift across the transformer. The decision on whether we use delta or star windings is dictated by the system requirements and whether we need a TP or TPN system. Congratulations for completing this section. You should now understand the differences between star and delta connected windings, why we use them in different parts of the electrical system, and how their physical arrangement can affect the transformer vector group. I have attached some questions on today's section to test your knowledge. In this section, we will look in detail at how the transformers are constructed and what devices we use to ensure that they're operating correctly. By the end of this section, you will know what is inside a typical transformer and what effect the operation of the cooling system has on the transformer rating. The aims of the course are to look at the control elements of distribution and transmission transformers, to look at the cooling system for a typical transmission level transformer, to look at the typical alarms that a transformer generates. The complexity of a transformer increases as the system voltage increases. Here we have a typical distribution system transformer. The first thing that we can see is the oil conservator. Transformers need oil as an insulating medium and to absorb and remove the waste heat generated. On the outside of the transformer you'll see radiators to disperse the waste heat that's been transferred to the oil. Inside the transformer we have an off-load tap changer which can change the output voltage in steps of 1%, with a variation from -5% of the system voltage to +5%. On top of the transformer, we have a winding temperature indicator gauge, or WTI. And finally, we have an oil level indicator, which gives an early indication whether oil is leaking from the transformer or not. Let's now look at the key elements of a transmission level transformer. Transmission level transformers are obviously a lot bigger than distribution transformers. The central item is the oil-filled tank which contains the windings. Because the transformer has a much higher capacity, we need free-standing radiators to dissipate the heat from the oil. we have an oil conservator, which is a tank on top of the transformer that allows any gas created inside the transformer to escape and allows for expansion and contraction of the oil as the transformer warms up and cools down. We have the high voltage bushings, where the HV supply is connected. We have the low voltage bushings, where the LV supply is connected. And finally, we have an on-load tap changer, which can change the output voltage in steps of 1%, with a typical range of -15% to +10% of the system voltage. If we look inside a transformer, the first thing we see is the magnetic core. The core ensures that the lines of magnetic flux circulate evenly between the phases and increases the efficiency of the transformer. On each leg of the core, we have the HV and LV windings. We have the red phase, yellow phase, and blue phase. Here's our transmission level transformer from before, with a tank and an external cooler bank. Let's look inside the transformer. Here we have the core and windings. We then have the low voltage bushings and the high voltage bushings. We have the mineral oil. The oil flows through pipes into the cooler bank. Radiators are provided to remove the excess heat. They can run in several possible scenarios. The first is ONAN, which is oil natural, air natural. In this condition, the oil absorbs the heat of the windings, rises to the top of the tank, and flows through the top pipe into the radiator. It then cools down as it flows through the small pipes inside the cooler bank. It then reaches the bottom of the cooler bank and flows back into the bottom of the transformer tank. Next we have OFAN, which is oil-forced air natural. In this scenario, pumps are operated on the pipes connecting the transformer tank to the cooler bank, and therefore the oil circulates more quickly through the cooler bank and cools down quicker. Finally, we have OFAF. This is oil-forced air-forced. In this scenario, in addition to the oil being pumped through the cooler bank, we have additional fans on the cooler bank, which cool down the oil quicker. The way the oil is circulated can make a significant difference to the electrical power rating of a transformer. A transformer that is operated in OFAF mode, i.e. oil-forced air-forced mode, may have double the electrical power rating of the same transformer operated in ONAN mode, i.e. oil natural air natural. Waste heat from the transformer is one of the main limiting factors in how much energy can pass through it at any one time. Transformers are some of the most efficient machines available, with most achieving 99% efficiency. But the 1% of the transformer rating that's lost through waste heat is still a substantial amount of energy, which has to be dissipated through the transformer oil and then onto the radiators and cooling fans. The cooling circuits are therefore a critical element, and losing them would mean that we can only feed half of the available power into the network, which could result in some customers losing power or having to reduce their loads. We also need to be aware of the ambient temperature. When a transformer is being operated in hot countries, the ability of the cooling equipment to dissipate the waste heat is severely limited, and the transformer rating may need to be overrated at the design stage to supply the required load. Just below the conservator on top of the transformer tank, you will see a Buchholz relay. When a fault occurs inside the transformer, we may get electrical arcing, which will start breaking down the oil into gaseous vapours. These will collect in the highest point of the transformer, which is the oil conservator. The Buchholz relay detects these gases. Gases flowing at a slow rate indicate that we may have a small insulation issue, and an alarm signal is sent to the SCADA system. When a full electrical fault occurs, we will get a surge of gas. When this occurs, the Buchholz relay will send a trip signal to the circuit breaker to disconnect the transformer from the system. High voltage networks use some of the most advanced communication and protection systems to quickly identify and clear any faults. But we always need a few old-fashioned mechanical devices in the system to provide a last resort backup when things go wrong. The Buchholz relay is one such device. We know that if a fault occurs inside the transformer, some gas will be generated in the oil. The bigger the fault, the more gas will be created, so it's a very reliable indicator of something going wrong inside the transformer. If you want to test the Buchholz relay, the best way is to use a foot pump to simulate the gas flow. Pumping slowly should set off the alarm contacts. Pumping quicker will set off the trip contacts. Another monitoring device you will find on transformers is the oil temperature indicator, or OTI. This is usually mounted on the top of distribution transformers and inside the local control cubicle, or LCC, for transmission level transformers. It gives an indication of the oil temperature inside the transformer. When the oil temperature reaches a preset level, an alarm will be sent to the SCADA system to indicate that there's a problem. On larger transformers, we also have a winding temperature indicator, or WTI. We don't really want to put a temperature sensor next to a high voltage winding. We know that the transformer winding temperature is directly related to the amount of current flowing in the windings and the length of time that this current has been flowing. To determine the temperature, the WTI relay is connected to its own current transformer to measure the level of current. This is then combined with a representative thermal model inside the WTI, which mimics how the transformer heats up over time. We normally have multiple alarm settings within the WTI should the temperature exceed a certain preset level. If the temperature exceeds a set threshold, the circuit breakers will be tripped and the transformer disconnected. The transformer alarm signals, Buchholz, winding temperature and oil temperature, are normally fed into flag relays, which repeat the signal and pass it on to other circuits. Here's a typical flag relay circuit fed from a Buchholz alarm contact. When the Buchholz alarm contact closes, the Buchholz gas flag relay energizes, closing the contacts and sending the signal off to the annunciator and the SCADA system. The transformer trip contacts, Buchholz or winding temperature, are normally hardwired into the circuit breaker trip circuit for security reasons. Here's the Buchholz trip contact connected straight to the trip coil. A series flag is used to provide any repeat contacts for SCADA. When the Buchholz trip contact closes, both the series flag relay and the trip coil are energized, and the signals forwarded on to the annunciator and SCADA system. Let's summarize what we learned today. The complexity of a transformer's control system increases as the system voltage increases. How we operate the cooling system for the transmission level transformer affects its electrical rating. Transmission level transformers have Buchholz, oil temperature, and winding temperature alarms and trips. Well done for completing this section. you should now understand all of the operational and control features of a transformer, and appreciate how important the cooling system is to the operation of the transformer. I've attached some questions on today's section to test your knowledge. Transformer tap changers are used to alter the voltage on the network. In this section, we will look at the main types of tap changers that we use and see how they are controlled. By the end of this section, you will appreciate the differences between no-load and on-load tap changers and understand the control circuits that we use to operate them. The aims of the course today are to introduce the principles behind transformer tap changers, to look at how no-load and on-load tap changers operate, to study the control circuits for on-load tap changers, tap changers are used to alter the voltage output of the transformer. Firstly, we have no-load tap changers. These are simple, hand-operated mechanical devices used on small distribution transformers. As the name suggests, these devices can only be operated when there is no current flowing and the load is disconnected. Next, we have on-load tap changers. These are automatic, SCADA-controlled devices that are fitted to most transmission transformers, and the load does not have to be disconnected whilst the tap changer is moving. The no-load tap changer works by adjusting the portion of the primary winding that's connected. This changes the ratio of the transformer and automatically alters the voltage that appears on the secondary winding. We only want to alter the secondary voltage by a small amount, either 5% or 10%, so we only need to change a small portion of the primary winding. Let's now zoom in on this small portion to see how the tap changer works. Here's a typical off-load tap changer. As you can see, at the moment we're on tap 1. On tap 1, we can see that the full primary winding is connected. To operate the tap changer, we firstly disconnect the load, then move the tap changer around to position 2 and reconnect the load. On position 2, we can see that a portion of the primary winding has been disconnected and the secondary voltage therefore increases. Let's move to position 3 now. And again, we reduce the portion of the primary winding that's connected. Again, the secondary voltage increases. To position 4 now. And finally position 5. When we get to position 5, there's a physical barrier to stop the tap changer being moved any further. Let's now go in the opposite direction. Tap 4, tap 3, tap 2, and finally back to tap 1, with the secondary voltage reducing after each tap. The majority of transformers provided on the distribution network are off-load tap changers, which tend to be set at a fixed tap for most of their working lives. Over time, if a section of the distribution network is becoming overloaded due to the types of load changing, or more customers being added, it may be required to increase the system voltage slightly to compensate for the strains on the network. All of the transformers feeding that part of the network will then be taken offline, one by one, and have their tap changers moved up a tap before being reconnected to the network. No-load tap changers, or NLTCs, tend to be used on small distribution transformers, where the voltage can be changed after the load has been disconnected. Their voltage operating range, typically plus or minus 3%, and number of steps tend to be quite small, typically 4 or 5. The no-load tap changer is normally located on the primary winding, as the current is less than the secondary winding, and the contacts that carry the current when the supply is restored can be smaller. On-load tap changers work on a similar principle, but resistors are inserted into the circuit whenever the tap changer moves from one position to the next. Here's an on-load tap changer on the secondary winding. As we can see, it's got 7 taps. Let's now energize the transformer. As we can see, on tap 1, the full secondary winding is connected. Let's now operate the tap changer. When the tap changer operates, the first stage is to connect 2 series resistors into the tap changer circuit. This allows us to change seamlessly from tap 1 to tap 2, while still carrying the current of the circuit. Once this has been achieved, we change over to tap 2. A smaller proportion of the secondary winding is now connected. The transformer ratio has been slightly changed, and the secondary voltage therefore reduces. Let's now initiate the tap changer to go from tap 2 to tap 3. The same sequence is now followed, and we move on to tap 3. On-load tap changers, or OLTCs, are used on larger distribution transformers and transmission level transformers. Their voltage operating range can go from plus 15% to minus 15%, and the number of steps can be extensive, typically 20 to 30. The on-load tap changer can be located on either the primary or secondary winding, as dealing with the voltages involved is more of an issue than dealing with the currents. The OLTC can be initiated from multiple sources, both inside the substation and remotely. The on-load tap changer can also be operated manually, using the handle inside the tap changer local control cubicle, or LCC. Here's a typical local control cubicle. As well as the operating handle, we can also see the tap position indicator, or TPI, which shows the tap that the transformer is on. The tap position indicator also sends an electrical signal back to the SCADA to give feedback on which tap the transformer is on. The on-load tap changer can be controlled from a variety of sources. These include raise tap or lower tap push buttons on the transformer local control cubicle, the voltage regulating relay, or VRR. We have a control switch on the transformer control panel in the substation control room. And finally, we have remote control via SCADA. As usual, the switches in the substation control room and the SCADA system are conditional on the position of the local remote switch. Here's a typical voltage regulating relay. Should the system voltage go above or below a threshold that's been set on the relay will automatically operate the tap changer. Let's look at a typical circuit for the tap changer raise controls. Here are the 4 control points that we identified previously. All these signals feed into the tap raise contactor. The first thing to note is that this circuit is fed from the 110 volt AC supply, which is normally derived directly from the transformer windings. As we can see, this tap changer has 29 taps. We have 2 conditional switches. The first one is a limit switch, Should the tap changer get to tap 29, this shuts down the circuit automatically to stop it going beyond the tap changer range. The next is a motion limit switch. This ensures that regardless of the signals, we only do one tap at a time. Let's now see how the tap raise circuit operates. Firstly, let's initiate a raise tap from the remote control center. This energizes the tap raise contactor, and the tap changer starts moving to the next tap up. Whilst the tap changer is moving, the motion limit switch opens, which disconnects the tap raise contactor until the tapping operation is complete. Let's now put the local remote switch into the local position and initiate a signal from the local raise switch in the substation control room. Again, the tap raise contactor energizes, the motion switch opens, and the tap changer completes the tap. The tap changer lower circuit is exactly the same, but just works in the opposite direction and lowers the taps. In my experience, on-load tap changers are one of the main fire risks in high-voltage substations, and I have lost several expensive transformers over the years when they've failed. The main issue is the integrity of the moving contacts inside the on-load tap changer, which deteriorate over time, especially on networks where the voltages need to be continually adjusted to stay within the thresholds required. To try and prevent these failures, on-load tap changers are subject to extensive maintenance programs, which kick in once the transformer has completed a certain number of taps. Let's summarize what we've learned today. No-load tap changers are simple devices that are used on smaller distribution transformers. On-load tap changers are complex devices that are used on transmission transformers. On-load tap changers can be controlled from multiple sources, including locally, automatically, and remotely. Congratulations for completing this section. You should now understand the key differences between no-load and on-load tap changers, know the different ways in which we can control them, and understand the circuitry that we use to operate them. I have attached some questions on today's section to test your knowledge. Transformer bias differential protection is the main relay that we use to look after the transformers on the network. By the end of this section, you will understand the basic operation of the relay and why we need to use a bias curve to ensure that it operates correctly under all conditions. The aims of the course today are: look at the main transformer protections that we use, introduce the principles of bias transformer differential protection, look in detail at how the bias curve operates, transformer protection relays are used to protect the most expensive and important device in the substation, i.e. the transformer. The main transformer protections that you will come across are the transformer alarms, including the Buchholz, winding temperature, and oil temperature. The earth fault relays, including the backup earth fault relay and the restricted earth fault relay. And finally, the main protection, which is normally a differential protection. As we've covered the transformer alarms and earth fault relays in a previous course, this module will focus on the differential protection relay. A differential relay is defined as a relay that operates when the phase difference of two or more identical electrical quantities exceeds a predetermined amount. This is the common symbol for the differential relay. And here's an actual relay. Most modern relays are multifunction and not only contain the differential relay element, but also the transformer alarms, indicated by the LEDs. Transformer differential protection works in the same way as any unit protection, and so makes the current flowing into and out of the transformer. If there is a difference, we know there's an issue. Here's a single-phase transformer. All we need to do is to put current transformers on the primary winding and the secondary winding, and connect them both to a differential relay to measure the difference in the currents. The current transformers form what we call a protection zone, with the transformer being monitored being inside the zone. As in any unit scheme, we need to use high-accuracy, Class X current transformers that all have the same ratio and characteristics. The circuits need to be slightly more complicated than a basic unit scheme, as the current magnitudes and phase angles may change from the primary to the secondary side of the transformer. Here we have a typical single-phase transformer with a 3:1 ratio. We have CTs on each of the live outputs. To compensate for the difference in the currents from the primary to the secondary side, we can use an interposing current transformer, with a ratio that's inverse to the turns ratio of the transformer. So in this case, because the transformer's got a 3:1 ratio, the interposing CT will have a 1:3 ratio. Here's a typical interposing CT. These can be complex and heavy devices, as they need to transform and carry the full current generated by the current transformers, under both normal and fault conditions. Interposing current transformers can be used to modify the secondary currents before they are fed into the differential relay. They can also be used to alter the phase angle to compensate for any vector change across the transformer. The unit protection principle is a very powerful one, which compares the phase currents going into a device with the phase currents flowing out. If they are both equal, then we know we have no faults on the device being monitored. As this is such a simple philosophy, unit protections are very reliable and can detect a fault on the equipment very quickly, something that is essential when protecting such an expensive device as a transformer. The unit principle can be used on a transformer, but we need to take into account the fact that the current vectors have been changed by the transformer, both in their magnitude due to the transformer turns ratio and also angle by the phase difference created by the transformer vector group. This does add some complexity to the scheme, but does not add too much additional delay. Here's a typical differential relay circuit. As usual, we ground the CTs in one position to deal with any transient voltages. Let's now energize the transformer. Under normal conditions, the currents generated by the primary and secondary CTs will operate in a circular motion and no current will flow through the differential relay. Let's see what happens if we have a fault inside the zone on the transformer. As soon as this happens, the current on the secondary winding will reverse direction. The currents generated by the primary and secondary current transformers are now in opposition, and current is forced through the transformer differential relay, which then operates, indicating a transformer differential fault. Let's now remove the fault and go back to a healthy condition. Let's now see what happens if we have an external fault outside the protection zone. Under this condition, both the primary and secondary current magnitudes increase substantially, and up to a certain current level, everything should be okay. However, if the current level increases further, The slight differences between the current transformer characteristics on the primary and secondary may be enough to generate a spill current, which may accidentally operate the differential relay. This is the main issue we face with transformer differential relays. To overcome this issue, we give the relay some biasing. Biasing is an additional check that we do before operating the relay, and make sure that the relay is genuinely seeing a fault rather than just a mismatch between the current transformer outputs. We achieve this by inhibiting the relay from tripping using a bias characteristic, which takes into account the amount of current flowing through the relay. Here's a typical bias curve. On the left-hand side of the graph we have the differential current, which is the difference in the currents flowing through the primary and secondary CTs. On the bottom of the graph we have the through or restrained current. This is calculated by adding the currents together and averaging them by dividing it by 2. Below the curve we have the don't trip zone, and above the curve we have the trip zone. Let's now see how this works in practice. Here we have our transformer from before. We've now added a new winding called the bias winding. This winding measures the value of the through current. Let's now add the bias characteristic so we can see what's going on. Let's now energize the transformer. As the primary and secondary currents go up and down, we move around the bottom of the don't trip zone. Let's now add a fault on the transformer inside the protection zone. As the secondary current now flows in the opposite direction to the primary current, the difference between the primary and secondary currents is now substantial. We quickly move into the trip zone. The relay operates and indicates a transformer differential fault. Let's now remove the fault and reset the relay. Let's now apply fault external to the protection zone. This time we move to the right-hand side of the characteristic, as the value of the primary and secondary currents increases substantially. There is a slight difference between these two currents, caused by the mismatch of the CTs, and some current flows through the operate winding. But because the bias curve is set at a steep angle above a certain level, this does not trip the relay. Therefore, by biasing the relay, we have made the differential relay less susceptible to through faults outside the protection zone. Transformers feed power into the network from the generating stations, and therefore also feed the network with the high currents that occur when a fault happens on the network. If transformer differential biasing wasn't used, all of the currents that pass through the transformer on the way to the fault on the network would destabilize the transformer differential protection and trick it into believing that the fault was actually on the transformer. The slope and pickup values of the biasing curve can be set very precisely, making it very easy to identify whether the fault is on the transformer or not, without adding too much additional time delay. When using differential relays on three-phase power transformers, we also need to take into account the following: any phase shift from the primary to the secondary winding, the magnetic inrush of the transformer, the transformer tap changer changing the transformer ratio, zero sequence currents destabilizing the relay on star delta and delta star transformers. Solutions for all of the above factors needs to be designed into the scheme. Let's summarize what we've learned today. A biased transformer differential relay detects the difference in currents between the primary and secondary outputs of the transformer. A bias curve is used to inhibit the relay so that the differential protection does not maloperate for heavy external faults. We need to consider several issues when implementing differential protection schemes, including the transformer ratio, the vector group, the magnetic inrush, and the impact of the tap changer. Congratulations for completing this section. You should now be familiar with the principles behind bias transformer differential protection, and understand why the bias curve is critical to the operation of the relay. I've attached some questions on today's section to test your knowledge. In this final section on transformers, we move from the theoretical side of transformer protection and start looking at how we make the physical connections. By the end of this section, you will understand how we connect the current transformers when we are applying transformer differential protection to star and delta connected windings. The aims of the course today are: see how we deal with the issues caused by the transformer vector group, ratio, tap changer, and magnetic inrush. Look at how we connect current transformers for star and delta connected windings. Look at how all the transformer protections operate together. Magnetic inrush happens when a transformer is first energized, and the power quickly flows into the transformer primary winding to magnetize the windings. The magnetic inrush may destabilize the differential relay, as the primary winding is energized before the secondary winding. This condition can last for a few seconds. Here's the typical magnetic inrush current waveform. As we can see, the waveform is quite deformed and reduces over time. Because of the deformed waveform, we know that the magnetic inrush characteristic has harmonic components. We can therefore block the magnetic inrush effect maloperating the differential relay by stopping the relay tripping if these harmonic components are detected. The transformer tap changer will change the ratio of the transformer as it alters the secondary output voltage from approximately plus 10% to minus 10%. We can normally deal with this slight change in the transformer ratio by adjusting the settings of the bias curve. Here's our standard transformer differential bias curve from the previous section. Because the tap changer changes the ratio of the transformer, it can create a small spill current. Here's the typical characteristic. As long as the tap changer mismatch characteristic can be kept in the no operate zone and below the bias curve, everything should be fine. If we need to, we can alter the settings of the relay to move the bias curve farther up the differential current axis. This will make sure that the tap changer doesn't trip the relay when it operates. In a star-delta or delta-star connected transformer, the zero sequence currents that flow in the star winding do not flow in the delta winding. This mismatch can destabilize the differential relay scheme. To resolve this problem, we connect the current transformers on delta windings in a star formation, and the current transformers on star windings in a delta formation. Let's look at the CT connections for a three-phase DD0 33 to 11 kV transformer. This is a delta-delta transformer with a turns ratio of 3 to 1. On delta windings, we connect the current transformers in a star formation, as we've done here. We connect the star points together and ground them at one point with a ground link. To compensate for the 33 to 11 kV transformer ratio, i.e. 3 to 1, we provide interposing current transformers on the secondary side. This is a DD0 transformer, so there are no issues with phase shift. Let's now look at a DY11 transformer. This time, the CTs are connected in star formation on the delta primary winding and delta formation on the star secondary winding. This arrangement will create a minus 30 degrees phase shift across the CTs, which will cancel out the plus 30 degrees phase shift created by the transformer itself. Because the CTs on the secondary side are connected in delta formation, we don't have a current transformer neutral. For the primary CTs, we connect the current transformer neutral point to the bottom of the operator winding on the differential relay and ground it at one point using a ground link. We will still need interposing CTs to correct the 3 to 1 transformer ratio. We will also need to do a ratio adjustment caused by the star-delta CT arrangement. And finally, a three-phase YY0 33 to 11 kV transformer. This time, the primary and secondary CTs are both connected in a delta configuration. This provides a benefit of eliminating any zero sequence currents that may arise. As we don't have any neutral connections, we ground the bottom of the differential relay operating coil to provide a current path. Some modern numerical relays do have the feature to compensate internally for the transformer star and delta windings. This is done via software adjustments inside the relay. Where this feature is available, interposing current transformers are not required, and the current transformers on the primary and secondary windings can both be connected in a star formation, regardless of the star-delta configuration on the transformer winding. Most substations have been developed over time, and you will see some very old circuits, with physical interposing current transformers inside, alongside more modern circuits with no interposing current transformers at all. Let's now combine the bias transformer differential protection with the earth fault protections discussed on the last course. Here's a 33 to 11 kV YY0 transformer. Firstly, let's add an earth fault relay on the neutral connection of the primary winding. This will detect any earth faults that appear on the network. Let's add a similar earth fault relay on the neutral connection of the secondary winding. Let's now add a restricted earth fault relay, monitoring the primary winding. This relay will detect any faults that occur on the primary winding. The relay forms a protection zone, encompassed by all the CTs. Let's now add a restricted earth fault relay on the secondary winding. Both of the individual windings are now protected. Finally, let's add our differential protection to protect the whole transformer. The differential relay will form a protection zone covering the whole area in between the primary and secondary CTs. We've now fully protected the transformer. Most modern transformer protection relays contain both the differential and restricted earth fault protections. When we utilize this type of relay, we simply feed all of the phase and neutral CT connections into the relay. As we can see, each of the protections performs a different task. The earth fault relay on the transformer neutral detects any earth fault current flowing into the transformer from the external network. If it goes above a certain level, we will trip the circuit breaker, disconnecting the network. The restricted earth fault relay protects an individual winding. whilst the differential protection protects the whole transformer. If we do get a fault on the transformer, we would expect to see one of the restricted earth fault protections operate at the same time as the differential protection. The restricted earth fault relay will tell us which of the windings have gone faulty. It's important to note that the protection zones formed by the restricted earth fault protection and differential protection overlap each other. This is an important feature of all protection systems, and ensures that every part of the transformer is protected. Let's summarise what we've learned today. We inhibit the transformer differential relay to stop it operating during magnetic inrush conditions. For star-connected transformer windings, we normally connect the CT secondaries in a delta formation. For delta-connected transformer windings, we normally connect the CT secondaries in a star formation. We have to design a specific differential protection scheme for each type of transformer, taking into account the transformer star-delta configuration, the vector group, and the transformer ratio. Congratulations for completing all of the sections covering transformers. You should now have a good understanding of all of the key features of transformers and how we use various equipments and relays to ensure that they're healthy. I've attached some questions on today's section to test your knowledge. This section introduces SCADA systems, which are used on most modern substations to provide control and monitoring functions. By the end of this section, you will understand the architecture of a SCADA system that we use on transmission substations and how we connect them to the primary plant and other equipments. The aims of the course today are to introduce the SCADA systems that we use inside substations, to look at the different inputs and outputs that connect to a typical SCADA system, to look at the different SCADA equipments that we use, SCADA is an acronym for Supervisory, Control and Data Acquisition Systems. They are used widely inside substations to monitor the status of the equipment and control the flow of electricity in the network. As usual, as the system voltage increases, the complexity of the SCADA system increases. Let's look at a typical SCADA system for a transmission network. Firstly, we have the control center. This is the central point in the system where the network is controlled. Connected to the control center, we have all the individual substations. Inside the control center, we will have multiple screens showing the status of all the equipment on the network, the power flowing through the system, and a readout of all the alarms and events that are occurring. Most electrical utilities have adopted SCADA systems to minimize the manpower required to operate the network and provide the ability to switch the network quickly when the loads change or a fault appears on the network. The loads on the network follow a predictable pattern for most days, with the loads increasing in the morning as people go to work and industry start up. They then stabilize throughout the day before picking up in the early evening as people get home and make some dinner, before tailing off as the day comes to an end. The network controller needs to anticipate these load increases in advance, as the generation capacity must always match the load required to stop the system voltage collapsing. There are many options for how the control center and substations communicate with each other. The most common way is to use fibre optic cable and use the facilities of the electrical network itself to transmit the information. Where we have power cables buried in the ground, we can install telecom ducts in the same trench to carry the SCADA signals. Here's a typical type of telecom duct that can be buried in the ground. Another way is to use an optical ground wire, or OPGW. A fibre optic cable is embedded in the ground wire for the transmission towers to carry the signals across the network. Here's a typical OPGW. You can clearly see the fibre optic cable inside the metallic ground wire. In specialised situations, where we don't have suitable overhead lines or cables, we can either use microwave antennas or radio masts to provide a radio signal. This will give us a direct link between the control centre and the substation. These are the typical signals that are exchanged between the SCADA system and the substation. Firstly, we have alarms to signal that something's gone wrong with the system. These include protection alarms, control alarms, and general alarms. Next, we have control signals from the SCADA system to the substation. These include equipment open and close signals, protection relay signals, tap changer controls to change the voltage, and building control signals, for example, to allow access to the substation. Next, we have measurements. These include system parameters, such as the level of power flowing and the levels of the voltages and currents. We have environmental measurements, such as the temperature inside the substation. Finally, we have indications from the substation into the SCADA system. These include equipment status, such as whether the circuit breakers are open or closed, the transformer tap changer positions, and general indications, such as whether the doors are open or not. Let's now look at the typical architecture for a substation SCADA system. Firstly, we have the remote control centre as seen previously. This connects via the communication channel to the substation communication room that holds all the panels that interface with the fibre optic system. This is where all the fibre optic communication cables are terminated. Connecting to the communication room, we have a local area network, or LAN. This connects all the computer systems together inside the substation. To the LAN, we connect many devices, including the Human-Machine Interface, or HMI. This is the PC or laptop that is used by the substation operators to control the equipment and monitor the alarms and systems. We then have additional equipment, such as laptops and printers. It's really important for the SCADA system that all the events and alarms are time-stamped so that we know exactly when they happened. To do this, we normally have a GPS time-synced switch, to which all the protection and control equipment is synchronized. We normally have a MIMIC control panel, from which the operators can open and close the equipment and monitor any alarms that come up on the station. To connect the MIMIC control panel to the LAN network, we use a remote terminal unit, or RTU. Remote terminal units, or RTUs, measure the analog and digital signals and convert them into data that can be fed onto the local area network. The substation local area networks and RTUs are a great way of collecting and processing the huge amount of data that is created by modern protection relays, and allow the network operator to focus in on a single relay on one circuit to see what's happening with the voltages and currents. All modern protection relays also store historical data after the fault occurs. The operator can easily connect remotely to the faulted relay to find out the timeline of what happened, so the fault can be quickly identified and the right action taken. We also connect the main substation equipment to the LAN network. Let's see how that's done. At the top we have the control room, which contains all of the MIPI control panels and the HMI interfaces. The interface between the control room and the substation are the RTU panels. These collect the thousands of signals that are generated by the primary plant and secondary systems. In most modern substations, the protection and control equipment can be connected via their own local area networks. This gives the central control system direct access to individual relays. Using this local area network, we can interrogate the relays directly to get information on status, protection alarms, and measurements of current and voltage. As well as the local area networks, we also have hardwired signals. The hundreds of control, alarm, and indication signals are all brought together in one place. These are cabinets full of terminals and are called SCADA marshalling kiosks. To connect the SCADA marshalling kiosk to the RTU panels, we use multi-pair cables. In these multi-pair cables, each wire has its unique colour. The SCADA marshalling kiosks are then hardwired to all of the equipment inside the substation, including relay panels, equipment local control cubicles, and substation systems, such as access control, fire detection, and building status. The normal way of connecting the SCADA marshalling kiosk to the equipment is using multi-core cabling. The cores tend to be 1.5 square millimeter copper, with each individual core being ferruled for identification purposes. Although the LANs and RTUs provide a great way of accessing the information on the substation, we still provide a hardwired system for all the main protection and control functions. The main reason we do this is to increase the security of the substation. As we've seen in the first protection course, we provide independent Main 1, Main 2 and backup protection systems for most transmission circuits, all fed from the lone DC supplies and systems. This level of redundancy is considered essential to maintain the security of the substation, and it's unlikely that hardwired systems will ever be fully replaced with a LAN and RTU-based option. Let's summarize what we learned today. SCADA systems monitor the health and status of the substation and allow it to be controlled from a remote control center. RTUs take analog and digital signals and convert them into data that can be fed onto a LAN network. The complexity of the SCADA system increases as the system voltage of the substation increases. Congratulations for completing the course. I hope you've had as much fun doing the course as I did writing it, and that you've learned some useful information that could help you with your careers. The next course in this series will focus on more advanced protection systems. I hope to see you there.